The dependency inversion principle gives us guidance to not design our high-level modules to depend on our low-level modules. But that sounds counterintuitive because it advises us to think about designs in a manner that's really the opposite of what we're used to. We're used to thinking about designs as top-down decompositions. We take a problem and we factor it into a high-level set of components that depend on a lower-level set of components. We often think of the high-level components as some kind of policy makers that are commanding a set of low-level components who are really carrying out all the real work. The problem with this approach is that it typically tightly couples our high-level components to our low-level ones. A symptom of this tight coupling is that it's often difficult to take that high-level component and then to go reuse it with a totally different underlying implementation of the low-level components. If our design is right, that's something we really should be able to do. The dependency inversion principle tells us to think of this in a different way by reversing the direction of this dependency. It tells us really two things. First, as we've said, high-level modules should not depend on low-level modules. Actually, both should depend on abstractions. And second, the principle offers that abstractions should not depend on details. Actually, details should depend on abstractions. Both of these statements require some explanation. Let's take a look at an example. Consider this remote control class. It has a click method that's called when a user indicates they want to control a television. The remote control depends on a lower level class called television, and that class offers two methods, turn TV on and turn TV off. So when the user clicks, the remote control click method has the logic to toggle between the on and off states by calling the turn TV on and turn TV off methods respectively. So this design looks straightforward enough, but there is room for improvement. For starters, this remote control controls only televisions, and more specifically, the television represented by the concrete television class. What if we want to control another kind of television, or even another kind of device with an on-off switch? It's not hard to notice that we have a high-level component, a remote control, depending directly on a low-level component, the concrete television class. So according to our principle, that can't be good. But how else would we approach this? Let's think through what the high-level policy for this design should be. What's the high-level policy? Well, as Robert Martin, the originator of this principle, says, it's the abstraction that underlies the application. So how's this for an improved high-level policy or abstraction? A remote control that can control anything with an on-off button. A TV, a light, a sprinkler system, and so on. Let's express that in our class diagram. To do that, we're going to create an abstraction for an on-off device. More specifically, we're going to create an interface on-off device that supports two methods, turn on and turn off. Next, we'll have our remote control depend on that abstraction by composing a remote control with an on-off device. And remember, before, the remote control depended on a concrete type, that television class. So now a remote control no longer depends on a low-level class. Instead, it actually depends on an abstraction. That's that on-off device interface. This goes the other way too. Remember that our principle also tells us that abstractions should not depend on details. Rather, details should depend on abstractions. Well, let's examine the television class now, and notice first that it implements the on-off device interface. No longer does it expose its proprietary turn TV on and turn TV off methods. So rather than our abstraction, the on-off device, depending on the low-level details of the television, that is, its turn TV on and turn TV off methods, it is the television that is depending on the high-level abstraction, that is, the turn on and turn off methods in the on-off device interface. So this is often the reverse of how we think of design, but by adhering to the dependency inversion principle, we really free our high-level components from being dependent on the details of low-level components. This really helps us avoid rigidity, fragility, and immobility. The dependency inversion principle tells us that all relationships between components should involve abstract classes and interfaces, not concrete classes. In doing so, helps us design software that's reusable and resilient to change because these abstractions allow the details between the components to remain isolated from each other.